Hi, my name is Dominik and I would like to introduce our work on reinforced scene-level plausibility for object pose refinement. The task of pose estimation is to determine an object's 3D location and 3D orientation with respect to the camera, potentially dealing with multiple interacting objects in the observed scene. However, the object of interest might only be partially observable due to occlusion. Depending on the sensor, noise and missing values further decrease the quality of the observation. Another error source is inaccurate instance segmentation, pruning too much of the foreground object or falsely including background objects. As a result, object pose estimates may be inaccurate and not align closely with the observation. This inaccuracy becomes even more striking when considering the physical plausibility of the estimated scene. Objects intersect each other, float in the air, or would not remain statically stable under their estimated pose. Our goal is thus to improve the accuracy of pose estimates by iterative refinement. We learn a policy that selects among discrete refinement steps in each iteration. The challenges just outlined are addressed by introducing a physical plausibility reward, a rendering-based pose scoring, and an outlier removal branch. Our experiments highlight the state-of-the-art accuracy of our approach in depth-based pose refinement. Given a pair of misaligned point clouds, we compute a global feature representation for each using a PointNet-like embedding. Based on the resulting state vector, two policy heads predict a discrete distribution over registration actions. As the registration converges, the policy selects smaller steps and eventually stops. We train the resulting agent by a combination of imitating an expert policy while maximizing a symmetry-aware alignment reward. We argue that consideration of physical plausibility enables us to resolve ambiguities due to partial observations. It allows to situate an object within the scene, and the interactions between the scene object restricts the space of admissible poses. To this end, we formulate physical plausibility with respect to three sets of critical points: intersecting, contact, and supported points. We are able to guide the scene-level refinement of the object poses by rewarding the agent if it reaches a plausible pose. Moreover, the signed distance between the target object and its environment is provided as an additional input channel. Due to inaccurate segmentation, the refinement may consider close-by objects or points sampled from the background. To contain this issue, we compute a rendering-based verification score for the object under the estimated pose in each iteration and return the overall best pose. The observed depth and normal images are compared to their rendered counterparts. As indicated by warmer, more yellow color in the illustration, the per pixel alignment iteratively increases during our refinement. We moreover introduce an outlier removal branch that prunes points from the max pooling operation that generates the global feature per point cloud. For our experiments, we crop the observed point clouds according to the segmentation masks predicted by PostCNN and use its pose estimates as initialization. We compare our depth-based refinement approach to a vanilla point-to-plane ICP implementation, point-to-plane ICP combined with the simulation-based verifying approach, the iterative collision check with ICP, and the multi-hypothesis ICP variant proposed with PostCNN. On the LINEMOD dataset, the increased accuracy of our approach is indicated by the recall for tighter thresholds of 5 and 2% of the object diameter. On the YCB-VIDEO dataset, we compute the recalls for a varying threshold and report the area under the resulting curve, outperforming competing methods by a significant margin. As compared to competing learning-based methods, our approach is able to achieve high accuracy using only 1/100th of the available real training data and without any additional synthetic data. Due to the global feature representation, we are able to reduce the number of point samples significantly, dealing computational efficiency for a slight decrease in accuracy. Our approach already significantly increases the accuracy of the estimated poses after one iteration, and after 5 iterations achieves a better result than the best compared depth-based approach that uses multiple pose hypotheses. Thanks for your attention.